webinars for railway industries, and this one today here is dedicated for electric powertrain simulations. Okay, so let's start with a quick introduction about this topic. The increasing railway traffic and the environmental issues represent a real challenge for the railway industries. And the main challenge here is to provide the required energy for trains while saving fuel and limiting the exhaust emissions. This is especially for non-electrified railway lines, where diesel-driven railway vehicles continue to play an important role for passenger transport. And that's why vehicle prototypes of different rail companies, as well as European and governmental projects, have been dealing with railway vehicle electrification. Table 1 here, taken from this reference, shows a compilation of results from the literature and the stated figures on fuel savings right here. And as you can see here, the main type of research used is a simulation-based study. Indeed, using electrified powertrain with embedded storage elements is an interesting technical solution, but this leads to handle different subsystems, different scenario and control strategies. And of course, regarding the overall system, we need to ensure the balancing between the performance and energy efficiency. We need to ensure the reliability and durability, as well as the comfort for passengers, and of course, the safety during operations. Consequently, this emphasizes system simulation needs. In this webinar, I will present the Simcenter system simulation capabilities to address simulation needs for the railway vehicle electrification. This is using Simcenter Amesim, which is an integrated, scalable system simulation platform. It allows system simulation engineers to virtually assess and optimize the mechatronic system's performance. Simcenter Amesim boosts the overall system engineering productivity from the early development stages until the final performance validation and controls calibration. You can make use of ready-to-use multi-physics libraries, which are combined with application and industry-oriented solutions. And Simcenter Amesim is an open environment which can be integrated into enterprise processes. It is easily coupled with major CAE, CAD, and control software packages. Okay, so in the following, I will first present the overall energy management simulation with the full railway vehicle simulation. So this is including the power sources and the main consumers. Then I will go through more details to present modeling capabilities for battery, for the fuel cell, and electric motor and inverter. So first, let's have an overview of the vehicle energy management simulation. The energy management study involves the consideration of the full railway vehicle simulation from power sources to main consumers. Consequently, this is a multi-physics simulation combining thermodynamic, mechanical, hydraulic, and electrical phenomena with, of course, a strong coupling between the different railway vehicle subsystems. And at the same time, to investigate the energy optimization of the main consumers, we need to estimate the losses which occurs in transmission in electrical, mechanical, and hydraulic components. And this is in addition to the energy required by the auxiliaries like the compressor and HVAC. For instance, this is an application case performed by Voith where we investigate the energy balance for an hybrid propulsion system. And the study here highlights that to get the lowest fuel consumption thanks to simulation, we need to put together the different subsystem models. Indeed, the energy management depends on the powertrain architecture. In this case, the hybrid propulsion system, we add an energy storage system here in order to store brake energy and support the diesel engine during acceleration phases. We can see here the estimated losses in the internal combustion engine as well as the estimated losses in the power transmission right here, also in the mechanical drivetrain and in the electric storage system, which is in this case a battery. And the fuel consumption here depends not only on these electrified powertrain components, but also it depends on the driving strategy to follow the mission profile. So that's to say, to perform the energy management simulation, system simulation solution is a key to ensure the results accuracy. And the best modeling workflow here is to start with simple modeling approaches, then increase the model complexity. Let me now present you these 3 demonstrators with different modeling levels. So I'm going to open Simcenter Amesim. So this is how Simcenter Amesim interface looks like. And the model development workflow is quite straightforward from the sketch mode here till the simulation mode. So first in the sketch mode, you can make use of different libraries you can see right here. For example, the electric motors and drives library. It offers a set of components, as you can see here. For example, this one, which is an electric drive and torque control component. You can easily drag and drop the components you need into the sketch and connect them together. So in this demonstrator, we represent a first level of electric drivetrain. It's comprised of an electrical power source right here, an electric drive and torque control component here, represented with functional approach. Here, this is the vehicle control unit. The Runway vehicle model is right here. The component here, in this component, we can define the emission profile and the ambient data. And this is the driver component, which computes accelerator, brake, and gear level position in order to follow the velocity target. So once we put the different components and connect them together, we can move to the submodel mode here, where we choose the modeling approach we want to use for each component. Afterward, we go to the parameter mode, where for each component we set the parameters. For example, this is a functional electric drive component. So this is an average model of the electric drive system, including the machine. It includes the inverter, the sensor, and control unit. And for the this component here, we can set the corresponding parameters using 2 characterization types. So the first one is the simple, where we define constant efficiency, constant maximum torque, maximum power, maximum rotor relative speed. And the second one here, we can define table or expression where the losses and the torque limits are a function of the operating conditions. So once we set the parameters, we can go to the simulation mode. Here, run the computation. So this one runs quite fast, and post-process the results, for example, to check that the vehicle velocity follows the vehicle speed target. Of course, for all the libraries, you can access to the documentation. If I click the help button here, we can open the library documentation. So it's ranked by libraries. For example, here we have the electric motors and drives library documentation. You can access the detailed documentation for all components right here, as well as for the different Python tools. So the Python tools here are application-oriented tools, which helps you setting up the model parameters with regard to the available data you have. And here you have a set of demonstrators which you can make use, and this is ranked by category. Now, if I go back to the Simcenter Amesim interface here, so that was a first level of electric drivetrain model. And we can move to a second level here, with a physics-based approach to represent the synchronous motor, the three-phase inverter, as well as the motor torque control. If we have a deeper look, for example, here, this synchronous motor, right here. So this is a permanent magnet synchronous machine using a quasi-static modeling approach. And for this model, if we have a look to corresponding parameters, since this is a physics-based model, we need inputs with regard to the machine parameters. So we need the magnetic characteristic, the stator resistance, as well as the iron losses. Of course, here to fill the parameters, it depends on the data available. So if you already have access to corresponding parameters, you can fill it directly into corresponding fields. Otherwise, you can make use of application-oriented tools. For example, this one here is the Simcenter Speed to Simcenter Amesim PMSM import tool, where in case you already have a project using Simcenter Speed, you can import corresponding project, and this tool will generate the right parameters for the Simcenter Amesim PMSM model. If I click here in the second tool, this is the same thing in case you already have a Simcenter MotorSolve project, and this tool will generate the right parameters to model Simcenter Amesim PMSM model. With regard to the inverter model here, so this inverter component is an average model of inverter for quasi-static loads, and corresponding losses can be defined whether from semiconductor characteristics, it could be constant efficiency, or user-defined here, where you can put expression or tables with precise losses. So once we set up the model, we can run the simulation and post-process. So the model here is compiling. So we can run the simulation right here. Then post-process the results. Here we can have a look to the motor energy losses right here. Same thing for the mechanical energy losses, as well as the converter energy losses. This is an overview of the global powertrain efficiency, and here we can post-process the energy consumption all along the emission profile. Now, these total energy losses here from the electric powertrain highlights the need to a thermal management system to cool down the electric powertrain components to ensure a good functioning under an optimized operating conditions. Now, in this level 2 model here, we have made an assumption to maintain corresponding temperature of the electric motor and the inverter at a constant temperature, which is 25 degrees Celsius. Of course, this is an assumption because in the real world, we need to add a coolant loop and address the thermal management control needs. So this is what we do in this level 3 model right here, if I make a zoom. So as you can see here, we added thermal components, so thermal capacitance here to represent the solid mass of the motor winding, the motor rotor and casing, motor cooling plate, and also the solid parts of the inverter. These thermal capacitance here computes the component temperature with regard to the incoming heat fluxes. So heat fluxes here, we have a source coming from the heat losses, whether from the machine or from the inverter. And we have the heat sink thanks to this coolant loop. So the coolant loop here is comprised of a radiator and fan. And here we can see that we have the cooling pump parts. Now, if I go back to the presentation mode right here, so I would like to share with you this use case from Voith Turbo. Maybe I can show you here I can share the link. So this is the article in Siemens webpage. So in this use case, Simcenter Amesim helped reducing the development and optimization time and costs. And the objective was to address the hybrid propulsion system complexity. Now, if we have a deeper view on corresponding article, so in this study, the authors analyzed the hybridization of a generic three-car diesel multiple unit here. One suburban and one regional surface profiles were simulated. And this is the general outline of the hybrid propulsion system. So the output from the virtual driver is used to control the RIPAC, which is comprised of an internal combustion engine, of power transmission, of some auxiliary systems, as well as the energy storage system right here. So three technologies are especially suited for onboard energy storage in railway vehicles. And the three of them were studied and simulated. The first one is a lithium-ion battery represented by an equivalent circuit model using Simcenter Amesim. The second one here is a double-layer capacitor represented by an equivalent circuit model too. And the third one is a flywheel energy storage system where the rotor of the flywheel is modeled as a rotary mass. So the authors ran different simulations using different power transmission systems, which are diesel hydromechanic with 4-speed automatic transmission, diesel hydromechanic with 6-speed automatic transmission, and diesel electric. And different electric storage systems were also virtually tested. First, a standard vehicle without electrification, then hybrid using the three possible electric storage systems, which are the double-layer capacitor, the flywheel, and the lithium-ion battery. So different driving strategies were also tested, A, B, C, and D here. And the fuel consumption in this table were compared, as you can see. So the lowest fuel consumption scenario is the one using hybrid diesel electric power transmission with the battery as the electric storage component. So this is a transition for the next part where we can have a deeper look at the battery modeling capabilities using Simcenter Amesim. The main library addressing battery simulation needs is the electric storage library. It offers battery components with different modeling approaches like equivalent circuit and electrochemical approaches. You can make use of validated cell model database for various lithium-ion chemistries, and you can also benefit from advanced capabilities like aging and thermal runaway modeling. Now, to ease the parameter setting, you can make use of different application-oriented tools depending on the data available from your side to set up the battery model parameters. For example, if I open again Simcenter Amesim, so the model here. Okay, so this is a battery cell model here, and this example represented using an equivalent circuit model. Here you can have a look to the different parameters required for this equivalent circuit model. And as you can see, we need electrical parameters, of course, depending on the model option we choose here. Now the question is how to set up these parameters. So different cases are possible. In case you already have corresponding tables, you can directly fill them in corresponding fields. And otherwise, you can make use of these application-oriented tools depending on the data you have. Now, in case you have no data, you can make use of this pre-calibrated tool right here and make use of the cell database provided here from this tool. So you can choose the technology of interest Corresponding parameters are already stored in the database, and you can just click on apply, and this tool will send automatically parameters to the battery model. Of course, these databases have been validated. We can have a look to the documentation right here. So as you can see in these tables, you have the database. So this is for the battery equivalent circuit model. Here we have the same thing for the electrochemical approach modeling. Here you can access to the different database, and which is of interest is that you can open the demo of experimental validation. For example, if I open this one, this is the documentation of the demo. Here we validate the simulation results against experiments using two profiles, an HPPC profile and a road profile. If I open a corresponding demonstrator, it should be the one right here. So in this demo, we ran two simulations to represent the two profiles, HPPC and road. And we compare simulation results for the three approaches over here against experiments. So the approaches are quasi-static model for the battery, dynamic model, and electrochemical model. We can have a look to the results. So this is the results with regard to the temperature for the HPPC profile right here. And here is for the road profile, and same thing for the voltage. Now, if I go back to the different tools, so that was to say that the database provided here have been validated against experiments, and you can have a look to corresponding demonstrators. Now, in case you don't have data with regard to the battery, but you have some requirements for the energy target or voltage target. In this case, you can make use of this second tool, the battery precising tool, where you can still choose one of the technologies available in the battery database, put the target with regard to the energy and voltage and power, and this tool will compute the battery characteristics and parameters to meet these targets. And same procedure, you click apply, and the tool will send the parameters to the model. I continue with another tool, the battery datasheet import tool. So this is in case you only have the datasheet of the battery, and this tool from the data available in the datasheet will compute the battery model parameters. Another case, in case you already have some test data, it could be HPPC data or pulse profile, you can make use of this battery electrothermal identification tool right here, and you can follow the step-by-step workflow. The idea is from some test data, or it could be electrochemical model, advanced model. So from this reference data, this tool will automatically generate the electrical and thermal parameters. I can show you the profile of a test. So here we need data with regard to the current, to the voltage, and optionally with the temperature. And the second step here, for example, the tool can compute the capacity and the state of charge of the cell. Then we can identify the electrical parameters, where you choose which test data will be used for these parameters identification, or the test can be used for the validation purpose. So electrical parameters are the following. We need to identify the open circuit voltage. For example, here we can show the results and compare with experiments. Ohmic resistance, so same procedure, and this tool will generate corresponding tables, as well as the diffusion parameters, where we can show, for example, the results with regard to the voltage to check the model consistency. So once these parameters are identified, we can generate corresponding tables depending on the temperature. and validate the results using other test data if possible. So other test data than the ones used for the identification. Same procedure for thermal parameters. So thermal parameters are the specific heat, the convective heat exchange coefficient, as well as the entropic coefficient. So we identify corresponding parameters, we generate corresponding tables and validate the results, for example, here by comparing the simulated temperature with the experimental one. So the idea here is to do it in an automatic way. You can directly export these parameters to the model and hence save engineering time. Now, if I go back to the presentation mode here, the benefit from these features is the possibility to size a battery pack with validated models of lithium-ion cells, then design a cooling subsystem, optimize the control strategy, or reduce the fuel consumption. And Simcenter Amesim offers degradation models for batteries. It offers an empirical model for the equivalent circuit approach and a physics-based model for the electrochemical approach. This is a computationally efficient model, which is well suited for more complex simulations, which are more like in the real-world conditions. For example, you can run live simulation, including the battery pack cooling system and other boundary conditions related to climate conditions or the Runway vehicle subsystems. Then you can check the overall life and warranty compliance. So this is by estimating the capacity fade and the impedance growth over many years. Okay, another challenge here regarding the battery thermal management is how to size the cooling system to avoid thermal runaway. The Simcenter Amesim offers a thermal runaway model, which together with the electrical model and boundary conditions at the system level, we simulate the pack response in real-world conditions, then check the safety compliance. So the thermal runaway model here simulates the four main exothermal reactions, which are the positive electrode decomposition, the SEE formation, the metastable SEE stabilization, and the electrolyte decomposition. The model also simulates the internal pressure increase, venting, and self-discharge, and you can make use of pre-calibrated parameters for the popular chemistries. And thanks to the system simulation capabilities, you can evaluate rapidly the impact of design variants on the thermal runaway of the battery pack. I can show you this demonstrator directly in Simcenter Amesim for thermal runaway, which is this one here. So in this demonstrator, we represent a battery module right here, where from this side we will heat up the cells in order to generate the thermal runaway. And this demonstrator, we run two simulations. In the first one, we define the distance between the cells equal to 2 millimeters. And in the second run here, we define the distance as 5 millimeters. Then we can compare the results. So here, if we have a look to the cell temperature, so these are the different cell temperature for the case where the space between cells is equal to 2 millimeters. And we can compare it with the case where the space between the cells is equal to 5 millimeters. And you can see here the impact of these design parameter on the thermal runaway propagation. Before I move to the next part, I would like to share with you this customer case. So the study was performed by a soft company to size a water cooling system to avoid thermal runaway propagation. This study was presented at the EV32 symposium, which took place in France. In the next part now, I will present the Simcenter Amesim fuel cell modeling capabilities. So the fuel cell library offers scalable fuel cell models from functional to semi-empirical and electrochemical models. You can also define reduced models. And thanks to the system simulation approach, you can include the different subsystems in the model. This is like the compressor, the humidifier, the cooling system, or valves, and the hydrogen tank. You can also benefit from the fuel cell parameter identification tool to set up and calibrate the fuel cell parameters. Now I can show you a demonstrator here using fuel cells. So this is, this one. So basically, this is the same demo as the level 3 I presented earlier in this webinar. We added an HVAC system, but in this webinar, I will not go through details with regard to HVAC simulation. This will be the topic for the next webinar next week. And we also added in this model a fuel cell to the electrified powertrain, if I make it. Here we can see the proton exchange membrane fuel cell. At the anode side, we represent the hydrogen tank. We represent also the hydrogen recirculation loop, including the compressor. And here at the cathode side, we represent the humidifier. We have an humidifier model. We have the air compressor and turbine models, as well as the condenser. So this is a hybrid powertrain, including the fuel cell in addition to the battery. We can run the simulation, check the hydrogen consumed, and of course, thanks to system simulation capabilities, we can go further to optimize the overall system energy console. Now I move to the next part to present the electric motor and inverter modeling capabilities. So the Simcenter Amesim electric motors and the drive solution enables to build up any electric powertrain architecture. It includes motor models for the main machine technologies, also scalable models for various simulation purposes like vehicle energy management or control optimization and validation. The library also offers easy to build power converter models and also ready-to-use control block. But you can, of course, include user-defined controls or make co-simulation with other softwares. The solution offers many links with specialized electromagnetic tools like Simcenter Speed, Simcenter MotorSolve, and GMag. So the benefit from this solution is to easily prepare different architecture and technologies, and this ensures fast computation time and enables the cooling system design. In the first demonstrator I presented earlier in this webinar, we represent the electric powertrain coolant loop. If I open Simcenter Amesim here, so that was the level 3 model here. So that was the coolant loop we added to ensure the thermal management of the electric machine and the inverter. And we can go further to simulate with more accuracy the inverter thermal behavior right here. So this is the demonstrator I'm going to show you here. So this is another level right here. Where we generate an FMU from Simcenter Amesim flow therm model. Just a quick introduction with regard to Simcenter flow therm. So Simcenter flow therm is a leading electronics cooling simulation software to accurately simulate thermal analysis. So we use this software to simulate a non-isothermal fluid flow for the inverter thermal simulation. And thanks to the FMU generated, we can accurately simulate in Simcenter Amesim the different temperature for the different diode for the inverter, as well as the cold plate surface temperature. Okay. Well, so that's all from my side. I hope you have a clearer view on the Simcenter Amesim solution to address the Runway vehicle simulation needs. So that was for electric powertrain modeling. Please let me know if you have any question. Also, here is my contact, so feel free to send me an email and I would be happy to help.
Thank you, Sana.